AP Physics. Last assignment in Chapter 4. Here's some review problems. Let's see, what do we have? 29, 35, 65, 83, and 117. Just a little selection of the three different types of problems that we're working with here. So 29 a projectile's launch is the speed is 5 times its speed at maximum height. This is a good one to do after we did 38 in the last assignment, because maybe we will remember now that the speed of a projectile at max height. What's going on there? Well, let's see. At max height, in the vertical direction, the maximum height is the maximum height because the vertical velocity is 0, right? The Vy, if you want to call it that. And in the horizontal direction, well, in the horizontal direction, the velocity is constant, so the velocity is just the same constant horizontal velocity that it always is. So that means at the maximum height, the speed of the projectile is the Pythagorized these, but of course this is just 0, so it's just a horizontal vector. It is the horizontal velocity. So what we're looking at here, if a projectile has a launch speed that is 5 times the speed at the max height, the speed at the max height is the constant horizontal velocity. So I think we have a triangle that looks like this. Right? This must be 5 times bigger than the constant horizontal velocity. And then we can find the angle from there. Right? Because let's see, we've got, this is adjacent to that, so you could set up cosine theta is equal to adjacent over hypotenuse, and those cancel, so we're just looking for theta is the cosine inverse of 1/5. That's a cute little problem, I think. That's about 78.5 degrees. All right, next is 35. A rifle that shoots bullets at 460 meters per second is to be aimed at a target that is 45.7 meters away. If the center of the target is level with the rifle, how high above the target must the rifle barrel be pointed so that the bullet hits dead center? So we got a delta x here of 45.7 meters, and I need to launch. That's an exaggeration, but even that is a little tricky to draw. The launch speed is going to be 460 meters per second, and I would like for the delta y, I want it to come and hit right there, so I want the delta y to be 0. Right? Okay, so let's see what we can do here. So I'm going to set up my vertical and horizontal. In the vertical direction, I have an acceleration of -g. My initial velocity is 460 times the cosine of whatever theta is. And let's see, I also know, do I know anything else in this direction? I do. The delta y, I would like it to hit the same height. That's 0. And I don't know anything about the final velocity. I guess it would be the opposite of this because of the symmetry there. And time is going to link these two together. So here I know that the constant horizontal velocity is, oops, put the wrong thing there. Were you jumping up and down in your chair there? Sorry. 460. So you can't really jump up and down in your chair. It's a weird expression. Maybe it's not a thing that people say. Maybe I'm the only person who says that. Maybe I should stop saying that. All right, so looks like a system of equations kind of job here, so I can get the link with the t's and solve for theta. So let's see, here got 1/2 at squared, sorry, delta y equals 1/2 at squared plus vit. 0 is equal to negative 4.9 t squared plus 460 sine theta t. I could divide one of the t's out there and get the equation t is equal to 460 sine theta over 4.9. You could divide that out if you want. And then over here, the relationship is delta x is equal to constant velocity times time. So 45.7 is equal to 460 cosine theta times time. I'm going to go ahead and just make this substitution here. 460 sine theta over 4.9. So let's see what we have. It looks like I have sine theta, cosine theta. I'm going to get everything else to the other side. So I got a 45.9 times 0.7, sorry, times 4.9, 45.7, show you what I'm doing, times 4.9, that's moving that up here, and then I'm going to divide by the 460s, divided by 460 squared is 0.00106, keeping 3 significant digits there. It would be a mistake, I think, to just stop there, right? 3 sig figs would be 0.00106. Okay, now there's you could do this by graphing if you wanted to. That's a little tricky maybe to do it that way because you're looking for a theta that's very close to 0, so it might be tricky to get the window right and everything. Or you could remember a trig identity. If I multiply both sides of this by 2, then this is the sine double angle formula. Then that's the same as sine 2 theta is equal to this. So that means that 2 theta is the sine inverse of that. So 0.0, let's see, sine inverse of 0.00212 is 2 theta is equal to 0.121, let's say. So theta is equal to 0.061 degrees. Now, I don't think that's the answer we're looking for because we want to know how high above the target should we aim. Okay, so we got that. Now I just need to make a triangle. It is a very long, skinny triangle. As this angle here is 0.061 degrees, and this, the leg here, is 45.7 meters, and I want to know what this little skinny bit is right here. So that's the opposite to this. So the tangent of 0.061 degrees is equal to this thing that I'm looking for, this little delta y, over 45.7. It's not to be confused with this delta y. This is the little how much higher you would have to aim. So what we're looking for is 45.7 times the tangent of 0.061. And that gives me 0.0487. And that would be SI units, so that'd be in meters. So you could report the answer like that, or you could say that it is 4.87 centimeters. The answer in the book is 4.84. That's just because of different choices in rounding somewhere along the way. So that is just fine if you got anything right close to that. All right. I think if you're wondering, like, oh boy, is that going to be like a question like that on the test? I think that that's pretty hard, that one that we just did. I don't think that something on the test would be quite that level of difficulty. That's a better homework problem than test problem. Test problems tend to be a little bit more straightforward. All right, 65. Looks like we got some uniform circular motion happening here. A purse at a radius of 2 meters and a wallet at a radius of 3 meters travel in uniform circular motion on the floor of a merry-go-round. That's weird. Somebody dropped their stuff. So let's see, the purse is at all the way at 3, and the wallet is at a radius of 2 meters. Okay. They are on the same radial line. Oh, I already blew that. And at one instant, the acceleration of the purse is 2,4. At that instant, in unit vector notation, what's the acceleration of the wallet? All right, so I think that probably I can get away with this here. So the magnitude of the acceleration would be 2,4. So the Pythagorized that, the square root of 20. Okay, so I know that, let's see, what are my equations here? Centripetal acceleration is equal to v squared over r, which is equal to omega squared times r. And actually, if you look at the, let's look at this for a second. As we go through the year and develop more mathematical models for describing this world, universe that we live in, mathematical models just means equations. As we develop more of those, we'll be interested in trying to develop our ability to do proportional reasoning. In other words, we want to be able to look at something like this and say, okay, if I changed this in such and such a way, how would that affect this? So if I changed this and kept this the same, what would happen? Is there like a linear relationship? Is there like a quadratic relationship? Is there a square root relationship? And what does that mean? So here we actually have this is a very easy question for us because the centripetal acceleration here, if we recognize that the omega, that because these two things are on the same merry-go-round, the omega for them is the same. Their speed is not the same, the v is not the same, because this one would be going a little bit slower. It's doing less of a circumference than the purse. But their omega is the same. They're on the same merry-go-round, so in terms of like radians per unit time, there's only one. It doesn't matter where you are in the merry-go-round. The angular velocity is the same, and that's why we're bothering to introduce that angular velocity at this point in the year. We're going to use it a lot more later when we look at more of the modeling with rotating objects. So anyway, one way of doing this problem, there are other ways of doing it for sure, but one way of doing it is just to say, according to this equation here, if this is left the same, then centripetal acceleration is directly proportional to radius, right? So that means which would do they give the... So they gave the acceleration of the purse, so we're decreasing that from 3 to 2, right? Basically, we're multiplying it by 2/3, you could think of. So that means that the centripetal acceleration is going to respond in exactly the same way because they are directly proportional to each other. Here's this thing to the first power equals a constant, because that's the same for both of them, times this to the first power. So that is direct proportionality. So it means if you multiply this by 2/3, that's going to change this by 2/3, and vice versa. Right? So that's one way to do it, to just look at that and say, okay, if the centripetal acceleration of this one is 2I plus 4J, then, oh, sorry, I got them, we know the one, this is the one for, I think I got them backwards. It doesn't change anything that I just said, but this is the purse, and this is the wallet. I think I had them the wrong way around. So the one that we know is for, this is the centripetal acceleration for this one. So to get from 2, if I increase the radius from 2 to 3, that's like multiplying by 3/2. So that will increase the centripetal acceleration by exactly that same factor. So that's 3I plus 6J meters per second squared. And that's one way to do that. The other way is to go through and find more stuff and actually do the math out. You can do it that way, but I'm going to leave you with this way of doing it. Okay? Let's see, 83 is next. Woman who can row a boat at 6.4 kilometers per hour in still water faces a long, straight river with a width of 6.4 kilometers. So here's the river. It's 6.4 kilometers across. And woman can row at 6.4 kilometers per hour. And the current is in the J direction. Downstream, current is going 3.2 kilometers per hour. If you're wondering, like, what is this problem about? This is like a vector kind of manipulation problem, like what we did early in the chapter, just to test our vector skills. Okay, and we got the positive I direction right across the river, so that's I. This is J. What angle should she point the boat at if she wants to get straight across? So if she wants to get from here to that point, then where should she point the boat? All right, let's answer that question first. And how long will it take? What we have to realize here is that the current is going to take her this way, so we have to add her velocity to the velocity of the current. So what we need to do, what she needs to do is aim somewhere down here, right? Because the current's going to push her this way. So her velocity is 6.4 kilometers per hour. And we have to add to that 3.2 kilometers per hour. And the sum of those two vectors, this and this, will result in her actual velocity, right? According to somebody who's like standing on the shore. So if she wants to end up straight across, she's got to row into the current a little bit so that she ends up going straight across, if that is her desire to do that. And then they want to know what angle. So let's find that angle. Well, actually, I mean, you could do it with your calculator, do the sine inverse of this over this, but that's just a half, so this is 30 degrees. And I guess we would say if she's looking across the river, would say point 30 degrees into the current. Something like that. And the book called it negative 30 degrees, so that's fine. B, how long is it going to take her to do that? Well, I would have to figure out her actual velocity here, which is the square root of 6.4 squared minus 3.2 squared. And this is 5.54 kilometers per hour is going to be her speed relative to an observer on the shore. And so she's going to do that. All right, I'm thinking about the constant velocity is equal to displacement over time, and it's 6.4 kilometers across the river. We want to know the time, so 6.4 divided by 5.54 is 1.16 hours. It's about an hour and 10 minutes. They have 69 minutes in the book. I'm fine if you leave it like that. C, what is the question here? How long will it take if instead she rows 3.2 kilometers down the river and then back to her starting point? So if she rows 3.2 kilometers this way and then back to her starting point. Okay, so let's see. When she's going a distance of 3.2 kilometers this way, how fast will she be going? Well, this is how fast she rows. So when she's going this way, her velocity is this way minus this from the current, right? If she was rowing this fast, it would look like to somebody standing on the shore that she was standing still, because she'd be going this fast, 3.2, but the river would be moving her 3.2 this way. So we have to add those together. So if she is rowing this way at 6.4, subtract this, she's going to be going 3.2 kilometers per hour. And then on her way back, her velocity is going to be 6.4 plus the current. And she still has to do the same 3.2 kilometers. So you can set up this equation and figure out the times, but pretty clear that takes an hour. Plus this takes a third of an hour. So an hour and 20 minutes. Part D, what if she rows up the river and then back to her starting point? Then what happens? Well, the math is all that if she goes up the river and back to her starting point, 3.2, it's the same as this. She just does this first and then this, so it's the same 80 minutes. At what angle to I should she point if she wants to cross the river in the shortest possible time? And what is that shortest possible time? Well, Whatever the river does, if she wants to maximize her like across the river velocity, she just has to point straight across the river, right? So 0 degrees, because if you think about what we did here, at any other angle, she's going to get less. This is going to be like a leg of a right triangle where her rowing speed is the hypotenuse. So at if this is any angle besides 0, this number, the across the river part of her velocity, is going to be smaller than 6.4. And the river's never going to help her. The river's always pushing this way. So if she wants to get across in the shortest amount of time, she just has to point herself straight across the river and then let the river do its thing, and we'll see where she lands. Which actually is not, I think, one of the questions. So for part F, the question was, E. So F, this is 0 degrees. She needs to just go straight across the river, 0 degrees to the I direction. And then F, how long is that shortest time? Well, if this is if she has all of her 6.4 kilometers per hour pointed across the river, and it's 6.4 kilometers across the river, it's going to take her 1 hour. All right. I think we have, is it just one more? I don't think I can fit it onto this sheet of paper. Let's see. How involved is 117? I don't remember. It's football player punts the football so that it will have a hang time of 4.5 seconds and land 46 meters away. If the ball leaves the player's foot 150 centimeters above the ground, what must be the magnitude and angle of the ball's initial velocity? I think I need more room than that, so we're reusing lots of paper here every day, trying to upcycle this paper as much as we can. There's a big pile of paper in front of me, not going to lie. Okay, so we have here's the ground. We've got a situation where football player is going to punt the ball. It's going to go a delta x of, was it 46 meters away? And the delta y, if we start at 1.5 meters, the delta y, it starts here and ends at the ground, so that you got to be real careful with these signs here. This isn't a super hard problem, but in my experience, that is a common mistake, to not get that negative sign. And we want a hang time, which means that's how long it's in the air, of 4.5 seconds. All right, and we want magnitude and angle of the ball's initial velocity. So let's set up our projectile motion problem. Acceleration is negative 9.8 meters per second squared. The initial velocity is, I don't know, I would like to know it. The time, final velocity, I don't think we're going to mess with that. Time is 4.5 seconds, and the delta y, how high it goes, I do not, oh no, the delta y I do know, it's negative 1.5. I don't know how high it goes, but that wouldn't belong here anyway, because that's not the time that goes with the peak. We could figure that out later if we wanted to, but I don't think it's part of this question. So here, Vx, the constant horizontal velocity, I would like to know that. The delta x is 46 meters, and the time is 4.5 seconds. So I think we're good here to find what that Vx is. Vx is equal to delta x over t when you have constant velocity. So 46 over 4.5, that's about 10.2 meters per second. And then here, I think we've got three things there, so I can find my Vi. So delta y is equal to 1/2 at squared plus VIT. There wasn't the finding something here and bringing it over to here because I knew the time in this case, and that's the one thing that is the same. So negative 1.5 is equal to negative 4.9 t squared plus, oops, I have the t. Oh, dang it. I'm just going to rewrite it. Negative 1.5 equals negative 4.9 times t squared plus VIT. I'm going to call that 4.5 times VI. And then have a little bit of math to do here. So negative 0.5 plus 4.9 times 4.5 squared divided by 4.5. So I'm getting a VI after doing a little algebra here of 21.7 meters per second. I'm just going to do something real quick. I'll let you know that if you got 22.4 here and you're like, oh, that's close enough. No, it's not close enough. That's what you get if you get the sign wrong on this. So 21.7 is what we're going with there. And we want to know the magnitude and angle of the ball's initial velocity. Well, I've got the two parts now, so I just need to put that vector together. I've got the 10.2 component here. That should really be a dotted line. And I've got the 21.7 here. And I'm interested in the angle and the magnitude of this. So let's do it. Pythagorize those. 10.2 squared plus 21.7 squared. We want a launch speed of 23 point, I guess 24.0 if I'm sticking with my 3 sig figs meters per second at an angle of tangent inverse of 21.7 over 10.2 is 64.8 degrees. And make sure that that agrees with the book. It does. So there you go. That's how you kick the ball.